Hey, kiddos. It was nice to see a lot of you during our first meeting. I'm so glad that we're giving this a try. This is a new thing for a lot of us, so please send me an email or shoot me a Google chat if you have some feedback about what's working and what's not working as we try and do some IB physics using virtual learning. So the idea here is that we'll have some time to meet every week, I hope, and I'll post a lesson or two every week. Please make sure that you're checking the Google Classroom and checking your PPS Gmail for communications. And please feel free to email me or send me a chat via Google Chat in your email if you've got any questions. Okay, so every week, once you do the lesson, you watch the video, try some problems, I am going to ask that you answer a question that will be on the Google Classroom, and you'll submit that to me as evidence that you are engaging with the lesson. Okay, so let's give this a shot and try our momentum lesson number 1. Some of this that we'll be doing today is a review of what we learned from the last time that we were together as a class. We just started momentum, and so I'm going to redefine some things about momentum, do a couple of problems, and then set you loose on some practice, okay? Okay, so happy momentum lesson number 1. So today's goals are to define momentum, use Newton's second law to derive a relationship between force, time, and momentum. We'll derive the law of conservation of momentum and then use impulse and momentum to justify an object's motion conceptually and analytically. You may notice that I'm in OneNote today, and that's just because if my computer is not connected to a smartboard, my smartboard program that I usually use to present my lessons will have this giant annoying watermark on it, and so I'm going to go ahead and work on OneNote, and then I can draw directly on my screen. All right, so momentum is a measure of an object's, I like to call it oomph, but it's inertia in motion. You'll notice my handwriting isn't much better on this than it is on the smartboard. I like to call inertia in motion like an object's oomph. Right, if you've got more mass and more motion, that object has more oomph. Okay, and I'm going to go ahead and switch over just to full screen here, I think. So momentum is equal to an object's mass, which is a measure of inertia, times its velocity. And when I'm using the word velocity, I'm indicating that we're working with vectors again, which means momentum is a vector. We're back here in vector land now. And so we've got momentum is equal to mass times velocity. And to indicate velocity, I'm going to use that little half arrow thing. We can't use lowercase m for momentum. That's already taken up by mass. And so we're going to instead use a lowercase letter p. And I'm going to put this little half arrow on there again to indicate that momentum is a vector. And we're just going to be working with momentum in a straight line. And so if you've got positive momentum values, that means you're going in one direction, and negative means the opposite direction. We won't have to work at angles in this curriculum. Okay. So just like the work energy theorem, where a force applied for a distance will change an object's kinetic energy, there's a corollary idea with momentum. So we can take a look at Newton's second law, which is F net equals ma, and we can get a relationship that tells us how we can apply a force to get an object's momentum to change. F net Remember, I'm going to leave the net subscript off here. We're assuming all of the forces are net forces. F net equals ma. Okay, and then we're going to expand acceleration. F net equals m. Acceleration fundamentally is an object's, change in velocity over time. Okay, and then let's rewrite that. What is mass times velocity? That's momentum. So that means a net force is an object's mass times change in velocity over time, which is the same as saying change in momentum over time. Okay, so this is actually a common way of writing Newton's second law. Okay, as net force is a change in momentum over time. Now let's expand this one more time, do a little algebra. Here, I'll write this in black again. We can multiply both sides by change in time, and you get change in time times net force is equal to a change in momentum. Okay, and obviously force is a vector. And so this equation is for what's called impulse. So a force, we know a net force exerted for any amount of time will accelerate an object, right? Change its velocity here. And so its momentum will change. So this is just yet another way of describing how net forces cause objects to accelerate. A common way of writing this, the official abbreviation for impulse is a capital J. I know. Joules is also a capital J, but we know that this isn't joules because it's a vector. Also, it's an abbreviation for a concept. It is not a unit that goes after a number. So the impulse is an object's force, a force exerted on an object for a certain amount of time, and that changes an object's momentum. We can write change in momentum, expand that out as mass times velocity final minus mass times velocity initial. Remember, the change in anything is final minus initial, and this is called impulse. All right, what are the units of impulse? Well, force times time is a Newton times a second. What are the units of momentum? Momentum is mass in kilograms times velocity, which is in meters per second. Are those the same thing? Well, what is a Newton? A Newton is a kilogram times a meter per second squared, right? Mass times acceleration times seconds. Oh, hey, look, this second and that second cancels out, and that is equal to a kilogram times a meter per second. All right, so I'm going to go ahead and box this whole business here. This is our impulse equation. All right. So let's do a little warm up here. If we had an impulse of 20 Newton seconds applied to a 5 kilogram wagon initially at rest, what's its final speed? Okay, so we've got an impulse of 20 Newton seconds. We've got a mass of 5 kilograms, and it was initially at rest. That means the initial velocity is 0. What is the final speed? Okay, so we could say one version of the impulse equation is impulse is equal to the change in momentum, mass times velocity final, minus mass times velocity initial. Cool. We know the initial velocity is 0, so this term cancels out. And so we can literally just say the impulse, 20 Newton seconds, is equal to the mass, 5.0 kilograms, times our unknown final velocity. And that means the final velocity is 4.0 meters per second. Easy peasy. All right. Now it looks like, oh yeah, something didn't load. So let's take a look at the law of conservation of momentum now. Just like the law of conservation of energy, we've got a law for conservation of momentum as well. And so let's take a look at Newton's third law. Newton's third law says objects in motion stay in motion. No, that's inertia. Just kidding. Newton's third law says every action has an equal and opposite reaction, right? And so just as a reminder, an action and a reaction are the forces objects are exerting on each other. And on the couple previous slides, we said that a force can be rewritten as the change in an object's momentum over time. So do you remember in our collisions educational play that we had like a red and a blue cart that were colliding? They were interacting with each other and each was exerting the same amount of force on each other. And so according to Newton's third law, we can say that the force that the blue car exerted was equal and opposite to the force the red car was exerting on the blue car. Okay? And so what is force? Well, it's the change in the blue car's momentum over time. And we've got that is equal and opposite to the change in the momentum of the red car, that's an R, over time. Okay, they're interacting for the same amount of time, so these times cancel out, and we see that the change in the momentum of the blue car must be equal and opposite to the change in momentum of the red car. Okay, so let's go ahead and write this out. So the change in momentum of the blue car would be massive. Let's not write that in red. Let's go ahead and keep that in black here. So we've got mass of the blue car times velocity final blue minus mass of the blue car times velocity initial of the blue car, right? That's the change in momentum of the blue car. And that's equal to the mass of the red car, velocity final red minus mass of the red car, velocity initial red. Okay, so this is the change in momentum of the red car. This is the change in momentum of the blue car. Now we're going to do some rearranging here. Boop, boop, boop. Okay, if we rearrange these, we can actually write this as, and let's not forget to include the fact that up here we said the change in momentum of the red car was negative. So we're going to make this negative and put this whole business in parentheses. Okay, now we're going to rearrange, and what we'll end up with is the mass of the blue car, velocity initial of the blue car, plus mass of the red car, velocity initial of the red car equals